right, here we go. The history of mathematics is marked by the discovery of special numbers like pi and I. Another special number is denoted by a letter. And you'll need to write this definition down that's in blue here. The natural base E, or the Euler number. Now what's really weird, and the reason why I read that bio first, was that I wanted you to get his name in your head, Euler. It's pronounced like O-I-L-E-R, but it's actually spelled E-U-L-E-R, but it's Euler, okay? So E is called the Euler number after Leonard Euler. So what we're going to do is we are going to discover what the Euler number is. So this is going to be neat. All right, so what I want you to do in this table is for the top row, I want you to put 10, 100, 1,000, 10,000, 100,000, 1 million, okay? And in the bottom row, we're going to use our calculators, and I'm going to refresh your memory on how to use the ask feature on the table, okay? So in that top row, we're just adding another 0 to the numbers. So let's go to our Y screen here. And in the Y sub 1, you're going to put parentheses, 1 plus, and we're going to use an X instead of an N. And so you're going to do 1 plus 1 divided by X, close the parenthesis to the X power. Then your calculator will allow you, because we don't want to have to scroll up to 1 million. Okay, that would take a really long time. So what we're going to do is we're going to do second window. Okay, second window gives you the table setup. And I hope you remember that this delta table, you don't have to always go by ones. You can go by tens, you can go by 20s, you can go by 50s, hundreds. You can even go by like 0.1. So you can go 0, 0.1, 0.2, 0.3, 0.4, depending on what you need. But under independent, remember, independent represents the X values. Dependent are Y values. And we want to go to second graph, which is the table, and we're going to enter the values in the table. So in your table now, write 2.5937, or however many decimals you can go. Then we're going to plug in 100. Write that in your table. Then do 1,000, 10,000, 100,000, all right, and I want to show you a couple things here. One, when I got to 1 million, even though I typed in a 1 with 6 zeros, there's not enough space here on the display of the calculator, so it converts it to calculator scientific notation. I hope you know, and you would never in a science class or in a math class write 1e6. That just stands for 1 times 10 to the 6, okay? The second thing I want to point out to you is right now it looks like the last 2 rows in the table are equal. And what I need to tell you is they're actually not the same. So I want you to use your right arrow, and I want you to get on top of that last number. Now, your calculator can only show you like 5 digits. And so, but if you get on top of the number, you see it's actually 2.71828046932. Now, arrow up 1, do you see, in fact, they're not the same. So when you get to decimals or bigger numbers and it starts to look like they're the same, move on top of the number and look down here at the bottom to see, is it actually the same? Okay, well what we just discovered is this is actually the value for E. Do you know how, like with pi is 3.14. Do you know where they came up with that number for pi? Do you know how it came about? Yeah, it has to do with the circumference and the diameter of a circle. What happened is mathematicians kept messing around with taking the circumference of the circle and dividing by the diameter, and they discovered no matter how big your circle circle, or how small the circle, every time you considered the circumference divided by its diameter, it was 3.14. That's like amazing, because that was done like hundreds and hundreds of years ago. They figured that out. If you do pre-calculus with me, we celebrate Pi Day. It's one of the things with honors, I do some very special things with them. We'll not only eat pie, but we do a quest for pi. We find out pi is in the Bible, okay? Very, very interesting, and we're going to find out where that is. But anyway, what I need you to know then is E is actually a number. It's 2.71828 blah, 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 okay? So it is now, now you have pi, you know I, and you now know E. So let's look at example 1. You're going to like this because this is nothing really new. We're just using the letter E with it. In letter A, if I have E squared times e to the 5th, my exponent rules apply. That's just a base. So it's e to the 7. In letter B, this becomes 4e to the 1st because 12 divided by 3 is 4. And if I subtract the exponents, I get e to the 1st. Now letter C, I believe we need to review this. I'm going to review some Algebra 1 exponent rules. If I take a times b to the m, that says you take a to the m times b to the m, because we struggled on our last test with this. So this means you have to remember to take 5 and square it, and e to the negative 3x and square it. Do you guys remember the test where it was like a 3? You did it to the variable, but you didn't do it to the 3, and you were supposed to cube that 3. All right, so that's 25, but now I'm going to use this exponent property in the next piece. If I have a to the m to the n, I need to multiply the exponents, so that's e to the negative 6x. And then the last property I need to use is the negative exponent property. You may not leave a negative exponent. So this is 25 over e to the 6x. Okay, so no negative exponents in our final answers. All right, example 2. We want to actually use our calculator to evaluate each of these. So what I want you to do is go back to your calculators, and don't forget that your graph calculator is on Ask. You'll want to turn it back on auto if you want to scroll up and down. But anyway, I want to show you there's 2 E buttons on your calculator. Do you see over here under the ln, there's an e to the x, and over on the opposite side, underneath the divided by, is an e. So you can use either one of them, but let me just point out kind of like when you would want to use each one. If I have something like 4e, I want to use this one because it's already to the 1st power. Okay? Now, if I have something like e to the 2x, this one automatically starts me with the exponent. That's the only difference. Okay? So see, I mean, I could still do e to the 4th. Oh, I didn't do e to the 4th before, but you know, do you know what I mean? All right, so let's try these. And you went around 3 decimals. Something I need to point out to TI-83 users. If you have the older calculator, when you do letter C, if you have more than one number, you have to put that whole exponent in a parenthesis. Those of us with the newer calculators, ours just does it for us. Okay? All right, check the board. Did you get the same answers I did?
How do you put in C?
C?
Yeah. Do you use the parentheses or not?
On yours, you shouldn't need it. You should just do E and do 3 divided by 4.
Okay.
Yeah. Yeah, you have a newer calculator. All right. Now go ahead and write down, and I apologize I didn't give you as much space on your notes, but we're actually going to draw 2 graphs here, so kind of scrunch right as small as you can because we have a lot to put down here. So now what you're going to find is this lesson is going to seem so easy compared to what we did in 7.1 and 7.2. We've already laid all the groundwork that we needed. It says a function of the form y equals a times e to the rx, okay, that's an r times x power, is called a natural base exponential function. If a is positive and r is positive, the function is exponential growth. If a is positive and r is negative, it's decay. So what I want to point out to you is that in 7.1 and 7.2, we were looking at y equals a times b to the x. And if a is positive, when b was greater than 1, it was growth. E is a number. You need to remember E is 2.71828. It's some number, and it's greater than 1, so that's why it's growth. Okay? So we're going to do two graphs down here. And we're going to graph the parent function, y equals e to the x. So we'll make an xy table from -2 to 2. Okay? And now go to your Y screen and clear out what you have. And now you're going to want to use the e to the x button that's over on the left. So you're going to do second e to the x. And let's suppose we just forgot what we had done just a moment ago, and I go to second graph, and I've got these wacky numbers in there that I need to remember. Uh-oh, I put it on ask, and I need to go second window, which is table setup, and put it back on auto. So I did that on purpose so that you could see what's going to happen to you sometimes. All right, now just fill in your table from -2 to 2. I'm going to go by 2's on my y-axis. Now remember, this is exponential growth, and we have a horizontal asymptote. So remember what I told you, you need to draw the horizontal asymptote on the graph, and you need to include it in the body of your work. Yes?
I accidentally deleted some.
Oh gosh, okay. When you go up here, oops. Okay. Okay, I fixed it for you, but you're gonna have to re-enter your Y stuff.
Okay.
When you're in your table, don't hit delete up there, okay?
Okay.
That's what happened. So go put your Y in and it should work from there. Okay, so back to this. I have a y-intercept that's at 0, 1, and there's no x-intercept. So remember, it's assumed you're doing all these things. The other thing, let's talk about domain and range. The domain is all real numbers because this is moving to the left forever and to the right forever. The range, remember with exponential growth and decay, it's either above your horizontal asymptote the whole time or below it. In this case, it's above, so it's y greater than 0. And you can't touch the horizontal asymptote. Okay?
Is the domain always going to be all real numbers?
Yes. For exponential growth and decay, domain is always all real numbers. Yes. All right, now in this one, I want us to graph y equals e to the negative x. and let's make an XY table from -2 to 2. And let me show you a feature on your calculator. I know I've shown you before, but maybe we need a little refresher. If you look at your Y screen, and all I need to do is insert a negative, move your arrow so it's flashing on top of the X, and you can press second delete. That's the insert. So you don't have to retype it and clear it, okay? You can use your insert key. Alright, and so there's your table, and you should notice all it's done is like flipped the table, hasn't it? Again, I'm going to go by 2's on the Y-axis, but 1's on the X-axis. So this graph is falling. It's a decay. I have a horizontal asymptote at y equals 0. The y-intercept is still 0, 1. So this one's a decay, where the first one was growth. So replacing x with negative x made it reverse. And we talked about this in, I think, 7.2. Do you remember where we did 2 to the negative x and we looked at 2 to the x? Do you notice this is a reflection over the y-axis, okay? So I want to point out I'm planting some pre-calculus seeds here, is that if you replace x with negative x, it reflects over the y-axis. Now let's pause a moment here and do a little exploration. Look at your calculators and let's go to the y screen and clear it out. And let's do the parent function e to the x, and then in y sub 2, let's do negative e to the x, okay? I don't mean the exponent, but I mean there's a negative out front. And then I'm going to do zoom 6 because I can't remember what screen I was using last. And I have e to the x. And then notice a negative out front reflects it over the x-axis. Something else I want to point out, it really is not touching the x-axis. If you press trace and you move left, look at those y values. I mean, it really is not 0, okay? But it gets smaller and smaller, and it looks closer and closer to it, okay? Alright, so now, example 3 says graph y equals 3e to the point 25x. This has not been shifted left or right, so we're going to use our standard table from -2 to 2. So what I want you to do is put this in your y screen, in your y sub 1, clear everything else out, make your table, and then graph it, because I think you've got all the tools that you need for this. So remember, the horizontal asymptote will always be y equals 0 unless you've shifted the graph up or down. Now something I want to point out about this one is that you actually have to go pretty far out to reach closer to that horizontal asymptote. Do you see that? It's a slow moving one. I have a y-intercept of 0, 3. There's still no x-intercept. My domain is all real numbers, and my range, remember the range is tied to your horizontal asymptote. It's above it, so it's y greater than 0. Something I noticed on homework is some of you are not drawing the horizontal asymptotes, And a few of you are not putting arrows. These do go forever and ever. When you draw it without the arrows, that means you're suggesting it's stopped there. So make sure you have arrows going on both ends of exponential. And this is growth, right? This is exponential growth. All right, any questions on letter A? All right, in B, how has this graph been shifted?
To right 1 up.
Good job. This is going right 2, up 1. So when I go to make my table, and I will look for this, I'm going to look at your table to see, do you understand the shift? I'm not going to start at -2. What number am I going to start with? 0, because I moved right 2. So you should go 0, 1, 2, 3, 4. So I'm looking that you're thinking, okay? You can still eventually get the graph if you started at -2, but you're going to have so many that are low, and it won't be interesting for a while. Since the graph has been shifted up 1, now my horizontal asymptote changed. I have a y-intercept at 0, 5.5. This still does not have an x-intercept. The domain is always all real numbers. And now the range changed. It's y greater than 1.
What is happening?
Yes.
I'm trying to put this in my calculator when I do something else.
Okay, let's look at how you entered it though. 8 negative. Oh, do you see you used the negative? So that made it times. That has to be a subtraction. Now try it. Yeah, and the TI-83s are a little tricky with making sure you get them in right. Everybody getting this? So make sure you guys are drawing horizontal asymptotes and indicating the equations. If it asks for domain and range, let's make sure we do it. Let's make sure we do that. Okay, because of time, we're going to skip the graph in example 4, but we're going to answer letter B. It says the length L in centimeters of a tiger shark can be modeled by this function. L equals 337 minus 276 e to the negative 0.178 t power, where t is the shark's age in years. Now on the homework, if you see a problem like this, we've been graphing where we say the standard table is -2 to 2. Now the domain here, and I guess maybe I should restate this to your question, it does not make any sense to say that the time, the age of the shark's age in years can't be negative, right? So the domain for a situation, you have to adjust it's case by case. So t, the domain would be greater than or equal to 0, so be careful with the situation. But anyway, if you want to estimate the length of the tiger shark that's 3 years old, let's see if we can do this and this is really a calculator crunch. Do 337, and you can do this in one row on your calculator. Just make sure you're entering the exponent correctly. I got 175.2 centimeters. You guys getting that? If not, let's figure out how are you entering it incorrectly on the calculator, okay? Everybody got it? 175.2.
I didn't.
Yeah.
180.
Oh, you entered 267 and it's 276.
Oh.
Yeah. All right, called continuous compounding. I've heard students over the years like to call this PERT. They're like, oh, okay, PERT. Where it's A equals P times e to the RT. P is your principal amount or initial amount you're investing. R is the interest rate as a decimal. And T is your time in years. Be careful if they give you months, like 18 months, that'd be 1.5 years. You wouldn't put 18 in for T. So, in example 5, it says you deposit $4,000 in an account that pays 6% annual interest compounded continuously. What is the balance after 5 years? Now, I need to point out to you that in the last lesson, we learned that other formula, but that's where you were compounding monthly, daily, annually. So you have to keep that one straight. The only time you use PERT is if you see the words compounded continuously. Okay? So this one is, so we started with $4,000 to the 0.06 times 5. So go ahead and punch that in your calculators. When you're done, check it at the board. I got $5,399.44.